Okay, so we are on the intersection of two lines today. What is in this? There we go. Okay. Can everyone see in here? Yep. Okay, we're good. All right. Yep. Excellent. Okay, so we're going to start off with the intersection of two lines the way we saw it in grade 10, and then we'll also do it using parametric equations because that's the way we're going to do it when we get to three space. So in two space, what are the possible ways a line can, or two lines can interact? So I've got my whiteboard here for those. If you remember them from grade 10, you can have, so this is just in two space, meaning on a flat plane. You could either have them intersecting at one point, and any lines that aren't parallel will intersect at one point. You could have them never intersecting, which is parallel lines. And who thinks they know the third possibility?
They can be perpendicular? I don't know.
That still counts as one point of intersection. So we can have one point of intersection, no intersection, or...
Does collinear count?
They'll be on top of each other?
Yes, exactly. So they could be exactly the same line on top of each other, which means they have a line of intersection, or every point is the same. Okay, so one point of intersection, parallel, so no intersection, or a line of intersection, or all of the points are intersection. Okay, so that's what we're going to copy into that first part there. So in two space, what are the possible ways two lines can interact? So you can have a point of intersection, POI, and that results if M2 does not equal KM1. So if the directions are not scalar multiples of each other, you automatically have a point of intersection in two space. Or we can have no intersection. And in that case, M2, the direction vectors are scalar multiples. And does anyone remember the test? How did we figure out whether they were this one, no intersection, or they were actually the same line and coincident? Line of intersection.
Check a point in it and see if.
Yeah, that's right. Line of intersection. So coincident is what we say geometrically, but it's a line of intersection. And again, that's if the direction vectors are scalar multiples. And how you decide between these two. So which one is it? Do they share a point? They share one point, they share all points. So as a point we know on one, also on the other. Do they share a point? That's how you differentiate between these two outcomes here. If the direction vectors are not scalar multiples, then we automatically know we have a point of intersection. We can go and find it. Okay, so in two space, there's three possible outcomes. In three space, we're going to see that there's four possible outcomes. But we're going to start off with two space. Okay, so find the intersection, question one, if it exists, of those two lines. So you can see these are in scalar form, if you remember back 2 weeks ago. So instead of looking at the equation and knowing what the direction vectors are, we look at the equation and we know what the normals are. Do you guys remember that? So the normal to this line is 2, 3. I'll call it normal 1. And the normal to this line is normal 2. And can you guys understand that if the normals are not scalar multiples, then neither will the direction vectors be? Does that make sense?
Yeah.
Yeah? Because, yeah, okay, good. So we can say that the second normal is not a scalar multiple of the first normal, just by looking at them. And that means in two space, that guarantees us a point of intersection. So we know that those two lines are going to intersect at a point. All we have to do is find it now. And we're going to use elimination. I know there was 3 methods that we learned in grade 10, but elimination is the one that goes nicest with 3 space. So we're going to practice it in 2 space as well. So I'm going to take some time to go through elimination for those of us that are a bit rusty on it. Now, if you have any questions about any of the steps and why I'm doing them, then please ask. So I'm going to call this equation 1 and this one equation 2. And elimination has to do with eliminating either the x variable or the y variable so that we can get the other one by itself. And what we're allowed to do is add or subtract these 2 equations, because when you're adding an equation already has left side and right side are equal. So if we're adding another equation to it, we're just adding the same thing to both sides. That's why elimination works. And we're allowed to multiply both sides of one or both of the equations by whatever number we choose, whatever constant we choose. So I see that I could eliminate x if I multiply equation 2 by 2, because then I'd have a 2x in both spots, and subtract. So that's what I'm going to do. I'm going to keep the first equation the same, except when we learned elimination in grade 10, we would have our x and y variables on one side and our constant on the other. And I like doing it that way. So if I think about, I want this negative 30 to be on the other side of the equals, I would add 30 to both sides. So I'm just changing how that equation looks. I added 30 to both sides, and now I've got my variables with their coefficients on one side, and I've got my constant on the other side. And I'm going to do the same thing here, but I'm also going to multiply equation 2 by 2 at the same time. So I'm going to multiply the x by 2, negative 2y by 2. I'm also going to multiply the 13 by 2, which makes it positive 26. But since I want it on the other side of the equals, it's going to be negative 26 over here. And then, because I want to eliminate x, I want to subtract. Same sign, subtract was a rule we kind of learned in grade 10 as well. So if I subtract those equations now, then I'm going to end up with 2x minus 2x is 0. So there's eliminated. I eliminated x. 3y subtract negative 4y is 7y. And 30 subtract negative 26 is positive 56. And if I divide both sides by 7, I get y equal to 8. So I know that at my point of intersection, the y value is 8, but a point of intersection in 2 space has an x value and a y value. So now I have to find x. So I can choose either of these equations or either of these equations to sub in to find x. I think I'll just choose this version of equation 1 over here. So I'm going to keep my 2x, replace y with 8. So still want to get x by itself, so I'm going to subtract 24 on both sides. And I get x is 3 if I divide both sides by 2. So then you're going to just do your therefore statement. Therefore, the point of intersection, so POI stands for point of intersection, is make sure you got the x first and the y second when you make your ordered pair. So the point of intersection is 3, 8. So that's a little review on elimination, the method of elimination to find the point of intersection. Okay, so now we're going to try one where we're given it in in either vector form. And this is the type of way that we're going to transfer into 3 space. So find the intersection if it exists of the 2 lines. So we've got our first direction vector here. M1 is 3, -2. And remember, we're in 2 space here because we've only got 2 components in each of our vectors. M2 is 2, 1. We can see that they're not scalar multiples. So we'd say M2 does not equal KM1. And that means in 2 space, we automatically have a point of intersection that we can solve for. So the first step is going to be to rewrite R1 in parametric form. So here's R1. Who can tell me what the parametrics of R1 are?
X equals 18 plus 3t.
Yep.
And y equals -2 minus 2t.
Perfect. Okay, so you want the parametrics of R1, and then we also want the parametrics of R2. So following that, the parametrics for R2, it's going to be x equals -5 plus 2u, and y equals 4 plus u. It's really important you remember to use 2 different parameters. So you don't want to use t for both of them. You're only going to have 1 variable, okay? When we set them equal to each other. So make sure if you use t for one set of parametrics, and say these ones were given to you in symmetric form where you didn't see a parameter, then remember to use a different letter. I often use t and u. The textbook often uses t and s, but s's sometimes look like 5s. So this is how we're going to find the point of intersection doing this way. So at the POI, do you guys agree that the x values from line 1 and line 2 are going to be the same as each other? And at the intersection, the y values from line 1 and line 2 are going to be equal to each other. So the x's are going to be equal and the y's are going to be equal at the point of intersection. So that's true. Since that's true, I can set the right side of each x equal to each other. So I can say at the point of intersection, 18 plus 3t is going to be equal to -5 plus 2u. And also the y values are going to be equal to each other. So -2 minus 2t is going to equal 4 plus u. So that's going to be true at the point of intersection. The x values and y values are going to equal each other for the 2 lines. The one spot where they'll be exactly the same for both. Okay, so now what I want to do is I want to take these equations and I want to make them look like, I know they're not x's and y's, but I want to make them look like this general form where I have a number x plus a number y, I know they're going to be t's and u's, equals a number. Okay, I want to rearrange them so they look like that. So I kind of think of that's my step 1 there. So in my step 2, I want the t's and u's on one side and then a number on the other. So I'm going to put my 3t first. I want the u on the other side of the equal sign, so I'm going to subtract 2u. And I want my constant on this side. I've got a -5 here. I want to move the 18 over, so I'm subtracting 18. So that should give me -23. Any questions on how to get 3t minus 2u equals -23 from this first equation here? Everybody's good? So that's going to be our equation number 1. And I want to do the same thing for this one. Now I'm going to show you what I would do. I like to have a positive number in front of my t's if I can help it. So I'm going to move the 2t over here. So it becomes positive 2t, but the u on this side was already positive. And then I'm going to move the 4 over here by subtracting it. -2 minus 4 is -6. So those would be my 2 equations and 2 unknowns. Any questions on how to get either of those 2 equations? Because it's important that you're able to do that. No. Okay, so now we either have to eliminate the t's or the u's. For me, I see that I only have to multiply equation 2 in order to eliminate u, so I'm going to eliminate u. But it would work either way. You could have, to eliminate t, you could have multiplied the first equation by 2 and the second one by 3. So to eliminate u, I'm going to keep the first equation the same. So I'm just going to write down equation 1 here. But I'm going to take equation 2 and multiply it by 2. So I'm going to have the 2 u's lined up, which means I have to multiply each part of equation 2 by 2. So 2t times 2 is 4t. Positive u times 2 is
Don't you
positive.
need to multiply it? Oh, I guess you can just add them after.
Yes,
rather than
right.
subtracting.
Yeah, that's what I was going to do. And -6 times 2 is -12. And as John said, because I have -2u and positive 2u, I'm going to decide to add these equations together to eliminate u. So again, because we might be adding or subtracting, make sure you show which one you're doing to eliminate. So 3t plus 4t is 7t. -2u plus 2u is 0. They're eliminated. Equals -23 plus -12. So that's -35. Divide both sides by 7. And we get t equal to -5. Now I'm going to go way back up here and find u. Because u is going to kind of be our check to make sure that we didn't make a mistake in our math anywhere. So I'm going to choose this equation to find u. So I'm going to replace t with -5. 2 times -5 plus u equals -6. And then if I want to get u by itself, I would add 10 to both sides. So I would end up getting u is 4. Now, it's not as easy as my point of intersection is my u and my t. Those are my parameters. My point of intersection is going to occur when t equals -5 and u equals 4. I only need to do one of those. So I might use my u parametrics to find my point of intersection. So in that case, x would be -5 plus 2 times our value of u, which is 8. Sorry, which is 4. I was already multiplying in my head here. And -5 plus 8 is 3. And then for y would be 4 plus u, but u is 4 also. So that would mean my POY is x being 3, y being 8. Now, you can check that your answer is right by using the t parametric in the t parametric equations. So my check is to make sure that when I sub -5 in for t, I also get 3 for x. 18 plus -15 is 3. And I also get 8. So that's going to be -2 plus 10. I also get 8 for y. So that's just a check. You don't need to do it, but you can do it. Okay? So this step kind of we added on here to find the point of intersection is different than if we're just given the scalar equation. But this is the way we're going to do it in 3 space.
Now, if you weren't doing the check, would you just need to get your t variable and then?
Right. Yeah. Correct. John.
Okay.
Yeah.
But I mean, it's good to be
T's-
sure if you want to get both variables.
Right. In two space, you would definitely only need to find one, but in 3 space, you have to find 2 because there's that 4th possibility, and that's what we're going to talk about right now. All right. So before we move on to 3 space, we're just going to kind of try to analyze what are the possible ways 2 lines could interact in 3 space. And we need 4 kind of sections of our. So can anyone come up with one way 2 lines could interact in 3 space? Okay, here's my 2 pens. Could there be a point of intersection? Yes,
I think there could be.
there could be. Okay, so let's do a point of intersection. So there could be a point of intersection. And in that case, the direction vectors would not be scalar multiples of each other. Any other possibilities for 3 space? There's 3 more. Can you think of another one?
They could, oh, sorry, you go, Emma.
They could not intersect at all.
And, okay, good. They could not intersect at all. So here's one, here's the other. See how they're not parallel, but they don't intersect at all because one's above the other one? But they're definitely not parallel. Does everyone see that? That's got a special name. It's called skew, okay? So they could be skew. So they never intersect at all. And I'm not great at drawing that one, but I kind of draw it like this, where I just leave a gap here. So again, the direction vectors are not scalar multiples of each other, but they never intersect. They kind of pass over top or underneath, right? So they never intersect in 3 space. So that's called skew. And notice that these 2 are related in that in both cases, the direction vectors are not scalar multiples. Now let's think about what if the direction vectors were scalar multiples, what's a possibility? If they're parallel, they could be parallel and distinct, right? No intersection. So they could be parallel and distinct. And that would be no intersection. Which is the same for skew lines. Skew lines have no intersection. Oops. No intersection for skew lines either. And then the last thing is they could be coincident lines. So they could be lines that just line up with each other, right? And they have a line of intersection. So they could be coinciding. So again, the direction vectors would be scalar multiples of each other. And they are coincident, which means there's a line of intersection. And you can use LOI for line of intersection. So if we look at our outcomes here, we could have a point of intersection or a line of intersection if we're intersecting. And there's also two ways that we could get no intersection: skew lines or parallel and distinct lines. So there's 4 possibilities in 3 space. So we're gonna kind of, first of all, we would look at the direction vectors to decide whether we're on this pathway or on this pathway. This pathway, again, to tell between these two, we see if they share a point. It's our test. If they do, they are coincident. If they don't, they're parallel and distinct. And then we're going to use the elimination route and see whether we have a point of intersection or skew lines if the direction vectors are not scalar multiples. Okay, so question 3, find the intersection if it exists of each pair of lines. If there's no intersection, differentiate between the lines being parallel and distinct or skew. All right, first step is to figure out the direction vector and compare them for each one. So for this one, it's easy. The direction vector is 3, 4, -2. For this one, we make sure it's in symmetric form. So that's good, that's good. Make this out of 1. So our direction vector is 2, 3, 1. And we can see that they're not scalar multiples. So we're going to say M2 is not a scalar multiple of M1. And then this time right therefore is going to be either we have a point of intersection or we have skew lines. So just basing it off of analyzing our direction vectors, we're either going to have a point of intersection or we're going to have skew lines. To tell that, we want to make parametric equations for each line. So for line 1, it's easy to make our parametric equations from a vector equation. We're going to have 3 of them. So x would equal -1 plus 3t. Y would equal 1 plus 4t. And z would equal 0, which we don't need to show, minus 2t. For R2, which is here, they gave it to us in symmetric form. Who wants to give me the parametric equations from symmetric form? And remember, don't use t, use a different parameter.
Could it be -1, x equals -1 plus 2u?
Yep.
Y equals 3u.
Yes, good.
And z equals -7 plus u.
Good. Does anyone have any questions about how John got those? We're all good? Okay, so instead of just saying at the point of intersection, we have to add on a little caveat. So we have to say at the point of intersection if it exists, because we may have skew lines here. We don't know yet. So if there were to be a point of intersection, that at that point of intersection, the x values would be equal to each other, the y values would be equal to each other, and the z values would be equal to each other. So we can make that statement that -1 plus 3t would have to equal -1 plus 2u. 1 plus 4t would have to equal 3u. And -2t would have to equal -7 plus u. So if there's a point of intersection, if one actually exists, then that has to be true. So kind of that's our first stage. Now I want to make it so my t's and u's are on one side and my constants are on the other for each of my three equations. So this is kind of just my rearrange step. So if I wanted to make this one prettier, I'd have my 3t minus 2u equals, so if I add this one over here, it's going to give me 0 on the right side, and that's going to be my equation 1. And then I want the next one to follow suit, so I want my 4t, and then minus 3u equals, so I have to subtract 1 to get it to the other side. So that would be my equation 2. And my equation 3, I want to have a positive number in front of t. I'm going to bring that to this side. So add 2t to both sides, keep the plus u on this side, and then add 7 to both sides to get it on the side by itself. And that's my equation 3. So we have 3 equations and only 2 unknowns. To solve a system, you only need to use 2 equations. The third equation is going to be our check. It's going to tell us whether we actually have a point of intersection or we have skew lines. So if we solve 2 out of the 3, if that u and t combination also works in the one we didn't use to solve with, then we have a point of intersection. If it doesn't work, then we have skew lines. So we have to decide whether we're going to solve 1 and 2, 1 and 3, or 2 and 3. Does anyone have something they see here where it might be easier to use a certain 2 of them?
I mean, 2 and 3 look all right. You could multiply 3 by 2 and then
yeah, so I definitely keep 3 in the mix because it's got a 1 in front of it, so it's easy to multiply to either cancel out with the 3u or the 2u. So John says 2 and 3, so let's do that. So then what I want us to do is I want us to lock away this one right now so we're not tempted to use it until the check. So I always draw a lock. You don't have to, but I always do. So that one's locked up right now, okay? So we're just solving 2 and 3. And we want to eliminate u. So we're going to keep equation 2 the same. And we're going to multiply equation 3 by 3, which means every single term in equation 3 we have to multiply by 3. So that's going to give us 6t plus 3u equals 21. And then because the negative 3u and positive 3u are opposite signs, we're going to add to eliminate u. So 4t plus 6t is 10t. Negative 3u plus 3u is 0. They're eliminated. Negative 1 plus 21 is 20. That works out nicely. Sometimes you will get fractions, but this worked out nicely, maybe because of the 2 that John chose. T equals 2 we got. So now I have to find the u that goes with t being 2, but I can only use either equation 2 or equation 3, okay? I can't use equation 1, that's my check equation. So I think I'm going to use equation 3. So I'm arrowing up. Oh, actually, I have room to find it below here, so I'll just keep working down the page here. So I'm going to find find U. So I'm using 2t plus U equals 7, replacing t with 2. And I end up getting U equal 3. So solving the system, just equations 2 and 3, I get that t is 2 and U is 3. So now to see whether there actually exists a point of intersection, we have to check if t is 2 and U is 3 also satisfies the first equation, the equation we locked up. So that's going to tell us if we have POI or skew. So I'm going to go up my page here. And now we're going to check POI or skew. And all we're going to do is a left side, right side check. So we're going to see if t is 2 and U is 3 satisfies this equation. So on the left side of the equation, we have 3t minus 2u. And on the right side, we have 0. And we're checking t being 2 and U being 3. And we end up getting 0. So now we know there's a point of intersection. Oh, sorry, I should write therefore left side equals right side, therefore point of intersection. So if left side didn't equal right side, then you'd write therefore skew lines and you'd be done the question. But since there's a point of intersection, we have to find it. So to find it, we can either take t equals 2 and sub it into our t parametrics, or we can choose U equals 3 and sub it into the U parametrics, and then we'd get the same point either way. So it's kind of up to you how you want to do it. I'm going to use the U parametrics with U being 3. If someone else wants to use the t and make sure that they get the same point, then we'll convince each other that it doesn't matter which ones you choose to do. If you're really careful, you can check using the other one if you want to be really convinced. So -1 plus 6 is 5. 3 times 3 is 9. -2 times, oops. Look, I went to the t parametric. That's a bad mistake. -7 plus 3 is -4. So therefore, point of intersection is 5, 9, -4.
It's the same for the t variables.
Awesome. Okay, so let's go through, like that's a lot of steps for one question. So let's go through and recap what we did here. We found our 2 direction vectors. We knew that they weren't scalar multiples, which narrowed us down to point of intersection or skew lines. We found parametrics for each set, and we made sure to use a different variable for our second set of parametrics, a different parameter, I should say. So don't use t for both of them. And then we said at the point of intersection, but we added on this if it exists because they could be skew lines. And then we set the x's equal to each other, the y's and the z's. Then we made the equations prettier by getting the t's and u's on one side and the constants on the other, carefully. Then we chose to solve 2 out of the 3 for t and u and kept the third one locked up. Once we had our t and u, we checked that it also satisfied the one we locked away because that's going to tell us whether we have a point of intersection or skew lines. So we did the check, it worked out, so we knew we had a point of intersection. And then we had to find the point of intersection by using either U is 3 in the U parametrics or T is 2 in the T parametrics. and then conclude with the therefore statement of what that point of intersection is. A lot of steps for that question. All right, go on to the next one. So 2 more lines to look at here. All right, so let's look at our direction vectors first. And I can see right away they're not scalar multiples. So it's going to be very similar to the one we just did. So the direction vectors are not scalar multiples. So therefore we either have a point of intersection or we have skew lines that never meet. Then we're going to do the parametrics for each line. So for the first line, the parametrics are x equals 2 plus t, y equals 1 minus t, z equals t. For our second line, the parametrics are x equals 3 plus 2u, y equals 3u, and z equals -1 minus u. And then we say at the point of intersection, if it exists, because it may not, the x values would be equal. So 2 plus t would equal 3 plus 2u. The y values would be equal, so 1 minus t would equal 3u. And the z values would be equal, so t would equal -1 minus u. Now we're going to rearrange them. So I want positives in front of my t, so t minus 2u equals 1 is going to be my equation 1. If I want to have a positive in front of my t in equation 2, does somebody know what my equation 2 would be?
Would t plus 3u equal 1 work?
Yes, good.
That kind of looks weird having the t minus 2u equal 1 and t plus 3u equal 1.
It does, doesn't it? So we might be thinking we might get skew lines here, but good observation. And then the last one, I would have t plus u equals -1. All right, does anyone have one they feel like they want to lock up? I'm going to lock 2. Just because the 3, all the other numbers look pretty small and easy. So that means we're going to solve 1 and 2. No, 1 and 3, sorry. And I can look, if I look at 1 and 3 right now, they both just have a plain t, so I can eliminate t right away. And I don't even have to do anything. I don't have to multiply either of the equations by anything. This is equation 3. And to eliminate t, I'm going to have to subtract because they have the same sign. So t minus t is 0. -2u minus u is -3u. 1 minus -1 is 2. And if I divide both sides by -3, I get u is -2/3. Now I have to find t. So I'm going to choose this equation 3 here. T plus u, so plus negative 2/3 equals -1. So I'm going to add 2/3 to both sides. Oops. I need a common denominator there. So I'm going to change -1 into -3/3. So I end up getting t is -1/3. So there's my t and there's my u. And now I have to check that in equation 2 and see if it works. Okay, so now we're going to check whether we have a POI. Check POI or skew. So I'm going to come up here and do that check. So on my left side of equation 2, I've got t plus 3u. And on my right side of equation 2, I've got 1. And the t I got was -1/3. And the u I got was -2/3. So I've got -1/3 minus 6/3, which gives me -7/3, which is not +1, right? So then we say, therefore, left side does not equal right side. Therefore, the lines are skew. And just to be really careful here and show that you know skew means there's no intersection. So we've got no intersection and the lines are skew. So again, I'm going to recap here what we did, and then I'll see if there's any questions. So we compared the direction vectors. They were not scalar multiples, so we know we had a point of intersection or skew lines. We found the parametrics for each using a different parameter. So one has t, one has u. Then at the point of intersection, if it exists, so again, this is good to write down here because it may be a point of intersection, it may be skew. Set the x's, y's, and z's equal to each other. Rearrange the equations so they've got the variables on one side and the constants on the other. Lock one of them away and solve the other system. The remaining two, solve that system. Eliminate your choice first. I eliminated t first because it looked easier. Find the other one. Once you've solved your system, check it in the one that you locked away. In this case, the left side and right side weren't equal, so we knew we had skew lines, which means no intersection. Any questions so far? Okay. All right, this time we're given both questions in symmetric form, or hopefully in symmetric form. Yeah, they are. The x's, y's, and z's are first. So first thing we're going to do is check the direction vectors. And they're not scalar multiples. So we either have a point of intersection or skew lines. So now we want to get the parametrics for each line. Volunteer to do the parametrics for the first line.
Would x equal 2 plus t,
Yep,
and then y is 1 plus 2t,
yep,
and z is 7 minus 2t.
good. Okay, and then a volunteer to do the parametrics for the second line.
I'm sure. Can someone do it? I mean, I could do it, I guess.
Sure, John.
I don't know. All right. Wow. So in the first equation, we have x equal to 1 plus 3u,
Yes.
and then y. It's a little shifty. It has 1 again
Yep,
plus 2u.
yep.
Maybe it's trying to copy x. And then z, you have a huge whopping 17.
I know, crazy.
Yeah. And then minus 4u.
Good. Okay. The next statement that you write down should say, at the point of intersection, if it exists. And I'm going to be sticky about that. So make sure you remember that in 3 space, because you may have one, you may not have one. All right, so then we can say, if it exists, 2 plus t has to equal 1 plus 3u. 1 plus 2t would have to equal 1 plus 2u. And 7 minus t, oops, 2t, 7 minus 2t would have to equal 17 minus 4u. And now you want to make them all pretty with positive t's. And your constants on the other side. This is where people make the most mistakes. So don't do it really quickly. Try to just think about it logically. Just a negative sign can be all the difference between finding that there is a point of intersection or accidentally finding their skew, or the other way around. So be careful. All right, so the next one, if I want a positive, it's going to be 2t minus 2u equals 0. And then here I'm bringing this over, so 2t minus 4u equals negative 10. Did everybody get those 3 equations?
Yep.
Yep. Okay, so I'm going to lock away equation 1 because I can see that the equation 2 and 3 both have 2 t's in them. Does that make sense? So I wouldn't have to do any multiplying to eliminate t. So this is my locked one. So I'm going to solve 2 and 3, and I'm going to eliminate t right away. And I can see that to eliminate the t's, I have to subtract because they have the same sign. So the 2 t's are going to subtract negative 2u, subtract negative 4u. So when you subtract a negative, you add, is going to give you positive 2u. And 0 subtract negative 10 is going to give you positive 10. Which means that u is going to be 5. And then I want to find t. So I'm going to use the first equation here. Sorry, this was equation 2 and this was equation 3. So 2t minus 2u equals 0. U is 5. So we're going to get t is 5 as well. Oops. So I got u is 5 and t is 5. So now we're going to check that in equation 1. We're going to check whether we have a point of intersection or whether we have skew lines. Did everyone get 5 and 5 for u and t?
Yes.
Yes. Okay, so here we're going to go and check. So check POI or skew, left side, right side check. So our left side for the equation we locked up was t minus 3u. My right side was -1. And t is 5 minus 3 times u, which is also 5.
Miss Northfoot,
Yeah?
would you be -5 or
Where?
you? Because
For
it was
you? 0 minus -10 is positive 10, right? 0, subtract -10.
Yeah, that's my bad.
It's okay. It's okay. Yeah, but those negative signs happen so often. So yeah, it's double check for sure. Okay, so you guys say these did not match?
Yeah, unfortunately, it doesn't look like they do.
Fortunately not. So therefore left side does not equal right side. Therefore no intersection. We have skew lines. All right, so again, setup, compare the direction vectors to narrow down your possibilities, get your parametrics. At the point of intersection, if it exists, set them equal to each other, make them pretty, choose 2 to solve. Once you've solved the 2, check it in the third one you didn't use. If left side equals right side, you have a point of intersection that you can go back and find using your original parametrics. If they're skew, then you're done. You have to say there's no intersection because they're skew. All right, we're on to our last question. All right, so here we're comparing these 2 lines to see whether they have a point of intersection skew, coincident or parallel and distinct. So M1 is 1, -4, 3, and M2 is 2, -8, 6. I think there's scalar multiples here. I think M2 is twice M1. Does everyone agree with that?
Yes.
All right, so that means we've got something different to write in our therefore here. So therefore, they're either parallel and distinct or coincident. And this one's set up really nicely because remember the test is a point we know on one on the other. And the way we test that point is parametric. So it's going to be great if we test if this point happens to be on this line. Does everyone see that? So our test to tell the difference between these 2 is going to be, is the point 8, 1, 3 also on R2? And then I'm going to spread my 3 parametrics out horizontally. So my first one is x equals 9 plus 2u. My second is y is -3 minus 8u. And my third is 6 plus z equals 6 plus 6u. And then I'm going to put 8 in for x, 1 in for y, 3 in for z, and see if I get the same u each time. If I do, then I've got coincident lines and a line of intersection. And if I don't, then I have two lines that are parallel and distinct. So I have to get u by itself in each of these. So I'm going to subtract 9 on both sides. So this one gives me u is negative 1/2. Add 3. This one also gives me u is negative 1/2. So it all comes down to the last one here. And so does this one. So since I get the same u for each one, then that means this point is also on this line. So if the point's on two lines and the lines are parallel, then they must be the same line. If they share a point and they're both in the same direction, then they have to be the same line. So therefore, the lines are coincident geometrically. They're the same line. But in terms of intersection, it means therefore there's a line of intersection. And you can state either of these as your line of intersection because really they're just two ways of writing the same thing. Line of intersection is r equals, I'll just use the vector form, 1, -4, 3. And if I hadn't got the same u's, I would have said the lines are parallel and distinct and there's no intersection.
So, Miss Northwood,
Yeah?
I'm just wondering, when we get to doing planes, I guess the planes are going to have lines of intersection.
They are. I have these big models that I use in the classroom, but on the weekend I made small ones that I can fit under my document camera so that you can kind of see how the normals look and all that stuff. So yeah, that's going to be Thursday and Friday, and there's little diagrams that you can cut and tape onto your lessons and your practices. So should be fun.
Cool.
Yeah, I'm excited. All right, is there any questions on today's lesson? Okay, I'm going to stop recording